so we can move to the next speaker, Valery. Your floor is yours.
Okay, now we just actually, so just moving from so the optical and soft X-ray band presented by Abi to the radio band, while I'll begin also with the EUV band. So first of all, so in the title of my talks, there is MHD seismology. So it's, no, well, I'm always tempted to say it's a new branch of solar physics. It's not so new, so it's been on the market for several decades, and it's the diagnostics of natural plasma environments with magnetohydrodynamic waves, which are now so just ubiquitous in the corona of the sun according to observation. So and any wave carries information about the medium so which supports the propagation of wave. So MHD seismology is one of the dedicated aims of the atmospheric imaging assembly on SDO. It is so a science objective of several future space missions. So it's named as one of key methods proposed for space weather development. So in the International Living with the Sun global roadmap for this decade. So, and in this talk, I'll address mainly the observational aspect of MHD seismology, because actually it is a combined science which is based upon elaborated theory and high precision observations. So for the non-say solar part of the audience, I'll just show you how it looks like, or well, at least one of classes of MHD oscillations which we see in the corona. So these EUV observations, you can see the solar limb here. You can see plasma loops seen as this elongated along the magnetic field, say loops of the plasma. And now if I run a movie, which is taken with a cadence of about 12 seconds, you can see that the loop shows transverse oscillations. If we process this video using motion magnification, so again, now concentrate on the right panel, is the same field of view, but processed, and you can see clearly this quasi-periodic persistent oscillations. So if we so put an observational slit across the oscillating loop, we can make a time distance plot, so which is clearly showing the oscillatory dynamics and allows us to measure the period, so the apparent projected amplitude, etc., etc. So if we say doing this, essentially, so the slide repeats what I just said. So we get in the time distance plot, we can best fit it with some guessed functional form. For example, it's a harmonic oscillation, so exponential damping, not necessarily, but for example, it could be used. So hence we determine parameters of this best fitting function. So, and using the parameters, we can deduce and obtain some important information about so the plasma structure, in this case, so the loop which supports these oscillations. So first of all, we need to identify the nature of this oscillation, and we see it as a standing mode, meaning so the whole loop oscillates in phase. So the highest amplitude is near the apex, meaning so the top of the loop, and so there are nodes of the oscillation near the foot points. So hence it looks like we are dealing with the second harmonic, or sorry, fundamental harmonic of the oscillation. To prove it, so we can make a statistics. So we have an ensemble of a number of loops oscillating with different periods. We can make this scaling of the oscillation period with the loop length, and it scales linearly. So which is consistent with the expectation for a standing wave. So hence the period of oscillation is linearly proportional to the wavelength, or in other words, the length of the oscillating loop. So the coefficient of the proportionality is a so-called King speed, which is about, in this case, 1300 kilometers per second, which in turn depends upon the Alfvén speed, which depends upon the magnetic field. So hence we get a tool for the estimation of the local magnetic field in the estimating plasma non-uniformity. So the estimating expression is shown here. So the magnetic field could be worked out if we know the period of oscillation, loop length, and also we need so the density of the plasma in the loop and the contrast of densities inside and outside the loop. It's a rather simple model, so it is based upon assumption that the loop cross-section is constant. There is no stratification, while all these, additional effects could be readily taken into account. In this case, of course, the formula would be more complicated, but it's not a big deal. So we can account for additional physical phenomena. So hence we're getting a rather, say, unique tool for the estimation of the magnetic field in the corona, where other techniques usually don't work. So in particular, extrapolation obviously has a lot of problems. So radio methods also have so their own shortcomings, and seismological estimation is at least a complementary, if not a unique tool for the estimation of the magnetic field. So this is just an example. So we made a pilot study, so trying to estimate so the alpine speed in different loops, which so are a part of the same active region. So here, so in the gray scale, we show the local value of the alpine speed. So it's the first map of alpine speeds constructed in an active region, constructed seismologically. So, and if as a follow-up study, so we can measure the density in each oscillating loop, and hence we can get the say map of the magnetic field. So which is very important, because in addition, so just kind of next step in this work could be estimation of the free magnetic energy. In other words, the non-potential magnetic energy, which is stored in this active region and is the maximum energy which could be released by this active region in the form of a flare or a coronal mass ejection. So which is very important and promising in the context of for a question of space weather extreme events. So not just summarizing, because obviously I have just half an hour. So MHD seismology these days, if we use the EUV band, seismology gives us the absolute value of the field. So it gives information about fine structuring of the density. In other words, so the estimation of the perpendicular scale. So it may constrain so the enigmatic coronal heating function. So it gives estimations of transport coefficients which are most likely affected by microturbulence and so appear in the form of anomalous viscosity, anomalous resistivity, etc. And as I mentioned, so the free magnetic energy. But in the EUV band, we are rather limited by the time resolution of available instrumentation. EUV observations are possible only from space, so hence usually we have just a single instrument, and it's difficult to exclude instrumental artifacts from the data. So hence we are looking at the radio band. In the radio band, we have intrinsically high time resolution. We're talking about, say hundreds of milliseconds as a routine time resolution in comparison with several seconds in the EUV band. Of course, we have poor or not at all spatial resolution, but it could be partly compensated by a small size of the emission source. So the signal is usually very strong. So the sun in a solar flare is very loud in the radio band. So the radio signal is directly linked with the electron concentration and the magnetic field, meaning it's not based upon any spectroscopy. So we are not talking about, say, iron of iron, ionized 12 times, etc. We're talking about just the electron concentration, meaning the plasma concentration. So we have ground-based facilities, so meaning we don't have problems with the telemetry. So the amount of information is not limited by anything. And also, so we have several instruments which could observe the same, say, phenomenon simultaneously, and they can be operating in the same band, so having the same parameters, meaning we can readily exclude any artifacts of the ionosphere, artifacts of individual instruments. So hence, actually, the radio band is very promising for seismology. So now I'll give you a few examples how it works. So first of all, it's a phenomenon which we know in the EUV band, which is rapidly propagating quasi-periodic fast wave trains. If you just concentrate your attention here, you see ripples which propagating outwards along the magnetic field, as you can see. It's possibly difficult to catch it by eye, so I'll show another event. So this is the image difference video. You can see so ripples propagating outwards. So they propagated the speed of about 1,000 kilometers per second. And so the typical periods are in the EUV band about 50 or 60 seconds, meaning they're just very near the threshold of time resolution of available instruments. So what about the radio band? So this is an example how it could be done. So here, so the data show time distance plots obtained in an EUV band. We can see a wave train as so the diagonal lanes in the time distance map. So it's a signal which is a wave train consisting of 5 or 6 oscillation cycles. And then if you look at the radio band without any spatial resolution, so we have simultaneous data obtained with Lermont and Beer's receivers, essentially. So what we see, so there are radio spikes which are labeled here as R1, R2, R3, R4, so which have the same period as the period of the fast wave train detected near the surface of the sun in EUV. So why we believe it is the same? Because actually, so the same, say, sequence of radio spikes in the same, well, bands, the same times is recorded simultaneously with 2 receivers. So, and the periodicity is the same as low down in EUV, meaning it's just possibly a proof of principle that so these signals could be seen in the radio band. So another example, so this is another say fast wave train, again seen in EUV. Again, I show the time distance plot. You can see those lanes, diagonal lanes corresponding to something propagating outwards. So, and then in the radio band, we have the same lanes, say in the radio spectrum this time. So the vertical axis here is the frequency again. And we can see that these wave trains, say, propagate because the diagonal features in the frequency spectrum corresponding to the signals propagating outwards the sun to lower and lower frequencies corresponding to lower and lower local electron plasma frequencies. So hence, say, higher heights, larger distances from the sun. Again, it's very consistent with what we see. So we can't see this, say, phenomenon simultaneously in the radio band and in EUV because, so we just look at different heights from the sun, but there is a very clear consistency between these observations. So it's another example. So here I should credit, so Dmitry, so the chair of the scientific organizing committee. So using LOFAR, so it was possible to say type 3 signal, so with striations of these various lanes also seen in the dynamic radio spectrum, so corresponding to the relatively low frequency, about 40 megahertz. So, and those striations so have this diagonal-like features which allow us to measure the propagation speed of those structures upwards. So first of all, how this signal could appear. So if we assume that it's a compressive wave which perturbs the density of the plasma, so hence assuming some stratified profile of the density shown here by the dashed line, so and perturbing the density by a wave, so with a low amplitude about just a few %, so we can see that if we integrate the signal in certain frequency channels, so frequency channels corresponding to local value of the electron plasma frequency determined by the local plasma frequency, so we are getting a clear, say, striation in the spectrum, so which corresponds to what we see. And then if we make forward modeling of this phenomenon, so we are getting a sequence of wave trains which resemble very much observations. Again, so it looks like so we are on the right track. So what we see in the radio band is consistent with what we should see in EUV. Now, in this case, actually, EUV signal was not available, but in the radio band, what we see is pretty consistent with this simple model. So then, just moving forward, those wave trains actually so have some interesting internal structure. So they're not monochromatic, so they're subject to frequency drift, which is determined by the dispersion of the fast magnetoacoustic waves guided by a waveguide along the magnetic field, and a prescribed, say, wavelet spectrum or predicted wavelet spectrum of such wave trains, so has a typical either crazy tadpole or boomerang shape, which is shown here. So can we see it in observations? Yes. So this is an illustration. So how using so data obtained with Andreev radio spectrograph long time ago. So we see a similar wavelet structure or dynamic spectrum structure corresponding to the boomerang shape perturbation of the radio intensity, which is connected with the perturbation of the local density of the plasma, so which corresponds to theoretical modeling. Again, so what we see in the radio band is pretty consistent with the theoretical expectations, which is another good news. So another mode of oscillation which we are very much interested in is so-called sausage oscillations. Sausage oscillations are axial perturbations of coronal loops, so which could be excited by different mechanisms, and essentially, so this say periodic variation of the cross-section affects the precipitation rate of non-thermal particles. If there are non-thermal particles in this flux tube, so they bounce between two magnetic mirrors, and the periodic variation of the say strand of the magnetic field opens and closes the magnetic mirrors, essentially moving them down and up. So hence it modulates the precipitation of non-thermal particles, which are seen there. So we call it Zaitsev-Stepanov mechanism proposed in 1982. So this modulation of the density of non-thermal particles leads to the modulation of the hard X-ray emission, gamma ray emission, and radio emission. Just an illustration, so just another example. So it's observations of such an oscillation, so made with Rotan 600. It's a transit telescope. So we see it so just at a certain point on the sky, and the sun is just passes through the elongated beam of the instrument, and just by sheer luck, it turned that during this transit, so the sun produced a solar flare, which occurred here. So which looked like the periodic, actually sudden increase in the intensity and variation of the polarization of the radio signal. So we also see some quasi-periodic pulsations, which may be attributed to sausage oscillations. Let's see whether it's consistent with observations, or well, other observations. So first of all, so this flare was a micro flare, or maybe even nano flare. It was visible in the radio band, but it was practically absent from soft X-ray. So the ghost signal for the time of this event so shows that actually it corresponds to this very small increase in the soft X-ray brightness. Essentially, the event is practically without any increase in the plasma temperature. So then, so this is the modulation of the polarization and modulation of the intensity. We can clearly see several cycles of the oscillation. Actually, in this case, if I am not confused, 8 or 9 cycles of the oscillations with the period of about half second. So the question is, if it is to be this sausage mode, we must have non-thermal electrons. And the existence of non-thermal electrons in this event is confirmed by Resi. So this is a Resi flare, so which has preceded the transit of this active region, which is shown here by this dashed vertical line. So meaning, so we can assume that the flare or micro flare occurred just before the transit, and by sheer luck we were just exactly in time to watch what was going on here. So this is the time of the radio observation. So then also, Resi spectrum shows the spectrum in green before the flare and in red during the flare. So we clearly see the increase in the number of non-thermal electrons, which is again what we need to have the interpretation in terms of sausage oscillations. And so the last bit is the EUV image of what is going on, or image EUV video. I'm just running the video, and now I'm stopping here. You can see sudden increase in the EUV brightness somewhere here, just exactly in time when the transit occurred. So with using this EUV instrument, we are not able to catch any sausage oscillations because periods are shorter than 1 second, while the cadence time of this instrument is 12 seconds. But at least we see that it was something dynamic going on there. So I'm just going to and fro in time, you can see it. So hence is another illustration that what we see in the radio band is consistent with what we see in EUV band, and at least those two bands are complementary. So having spatial resolution, I'm showing how a flare looks like if we see it with spatial resolution in the radio band. It's a so-called Coronal map obtained with the Novi-Yama radio heliograph, which unfortunately is decommissioned now. So the whole loop is filled in with non-thermal electrons, So the density of non-thermal electrons changes in time, so showing a quasi-periodic pulsating pattern with a period of about 16 seconds in this case, and just making the correlation of the radio signals at different pixels, we are getting this clear off-limb loop, so which corresponds to the source of the radio emission. So the width actually of this loop, so obtained by this technique, is shorter than the beam size of the instrument. It's not shown here, but actually it's about like that. So which is another interesting, say, way to process the data. And finishing this, so just another manifestation of sausage oscillations, this time also in the dynamic radio spectrum. So the zebra patterns, so famous, say, dynamic radio burst phenomenon. So if you look at the zebra pattern, we see some oscillatory wiggles, so corresponding to different variation of the lane frequency in time. So typical period is also about 1 second. And then if we just look at this dynamics, we can attribute it to the variation of the local electron cyclotron frequency and electron plasma frequency, which in turn are modulated by perturbation of the density and the magnetic field in a sausage wave. So, and if we make a simulation, if we just interpret the zebra pattern formation in terms of the double plasma resonant mechanism, so we can readily produce wiggles which correspond to the variation of the density and magnetic field in a sausage oscillation. Again, it looks like on the right track, and so what we see is consistent with expectations. So then just absolutely kind of final bit. So the slow magnetoacoustic oscillations mentioned by Abi. So long periods, large amplitudes, very well seen in EUV band. So, and another good news is we see similar oscillations in the radio band too. So this is an example when we see a flare, so in which we see oscillations in EUV from space and with Nobuyama radioheliograph from ground. And so the oscillatory patterns on the left, it's so the Nobuyama signal, on the right, it's the AIA signal in EUV. So the parameters of the oscillatory pattern are the same. It's a very good news because we clearly see in the radio band what we want to see in EUV. And in the radio, so this event could be seen without any spatial resolution, meaning it could be seen in stellar flares. While in solar flares, of course, the modulation of the UV signal is very small. And if you see the sun as a star, we clearly don't get this signal. So hence, we first of all link what we see in EUV with what we see in radio, and making one step forward, we see that this technique could be used also in application to stellar flares. So Abi has already described this scaling. So it's a very interesting research avenue, which is based upon the exploitation of the solar stellar analogy and the similarity of the scaling of parameters of quasi-periodic pulsations of the slow magnetoacoustic oscillation type. So in solar flares and in stellar flares, both observed in soft X-rays, clearly suggest that they could be the same physical mechanisms responsible for this scaling. No, by the way, I should possibly mention that this linear scaling of the damping time with the oscillation period is a non-trivial. It's not predicted theoretically. It's something which we get empirically, and we're still struggling explaining the scaling theoretically. So my conclusions, and I think possibly I just stop showing this slide, and I'm open to questions. Thank you.
Thanks a lot. And I think first question from Abi, and Abi, could you ask?
Hi, Valery. At one place you have shown a forward model, okay? So there UV emissions are well distributed with time, but the radio emissions were localized over the regular interval. So is there anything specific while you are comparing both the emissions like UV and radio emissions?
No, in the ideal world, yes, but the problem is usually in the radio we have very poor spatial resolution. We expect to have very decent spatial resolution of about 1 arc second with the square kilometer array when it is commissioned, but not now. So hence, I would rather consider these two approaches as complementary. So okay. In EUV, we have spatial resolution, in radio, we have time resolution, and we clearly have the overlap of results obtained in these two different bands. So hence, from this kind of common territory, we can proceed to smaller scales or to smaller spatial scales or smaller time scales. But a very important kind of result is that, so we see similar phenomena when we have this overlap.
Okay. Yeah, thank you.
Thanks a lot. Krishna have a question.
Yes. Hi, Valery. Thanks for the nice overview. So I think you mentioned at some point, if you look as the sun as a star from UV, because the modulation amplitude is low, you will not see these sloshing type or slow wave oscillations, whereas in radio, you can see them. Do we understand why the difference, the modulation amplitude is larger in radio and why it is not?
Oh, no, it's just, yes, I see the question is simply connected with the nature of the radiation, because if you have a flare, so the sun brightness in EUV increases by a fraction of 1%, right?
Mm-hmm.
While in the radio band, so the brightness of the sun increases by several orders of magnitude.
Ah, okay. Mm-hmm.
That's it.
Okay, thanks.
Thanks a lot. I think there is no question, and I think we can continue discussion at the end of the meeting.